Okay, hi. I want to go over our last homework, or the one that we have now regarding sampling distribution of means. Imagine if I had a jar, we were all sitting in here, and I had a jar full of pennies. And I had, before I came into the classroom, I had taken the year of every single penny that it was made, and I had put that on an Excel spreadsheet and estimated the average or the mean. And then I passed the jar in the class, and I have all of you select 10 pennies out of this huge jar, and I ask you to calculate the mean. This is sort of the concept here. If I were to take everyone in the class, all 45, everyone's estimate of the mean, your sample, and I took those means and averaged them together, there is a theory that says in the long run, that mean that we calculate with all the samples would be the same as if we had actually sampled the entire population. And that's where statistics really comes from. The idea of using statistics where you can sample a small population and then make predictions about a larger population is phenomenal, because prior to this, people would think that you needed to sample every single individual person. And sometimes in research, that could be tens of thousands of people. Now, with this, we can sample a random sample, assuming they're random, and we're always going to assume that they are, and we can make estimates about the general population from that. All right, let me start with number one. So a frequency distribution of a large number of random samples, means which have been drawn from the population, that's called the sampling distribution of the means. For example, like when I pass the jar around. All right, two, if I'm going to compare the 95% confidence interval with the 99% confidence interval. So assuming I have a confidence interval, this would be 95. When I have a 95% confidence interval, that means that inside of here, this is 95. And I'm basically left with 5% of the tails. We could say 5% of the tails. So this would be equal to 2.5, and this would be equal to 2.5. If I were to go from a 95 to a 99% confidence interval, I am basically widening my confidence interval. And instead of having 2.5 on it in the tail, I'm only left with 1% here. So I'm going to have 0.05% in each tail. So as you can see, when I go from a 95 to a 99, I am actually widening. So the answer to number 2 is going to be false. Pollsters sometimes refer to sampling error as the margin of error, and it's kind of important right now. We've got the elections going on, and so you'll sometimes see, maybe I'll post an article, if I can find one, regarding how the election is looking so far. That the margin of error is usually the statistical difference between by them randomly asking a couple people who they're going to vote for versus what we expect whomever to be elected in November. All right, number 4, regardless of how well the sampling plan has been designed, with the researcher's best intentions, no cheating, no mistakes, and the difference between the sample mean and the population mean is known as the sampling error. No matter what, you will never be able to get rid of sampling error. All right, number 5, researchers that analyze a portion of an entire population is called a sample. You're just looking at a subset of people. Number 6, researchers deal with an extra amount of uncertainty in estimating the standard error of the mean with a distribution known as the t. Last module, we were using the z table because we had the whole entire population, meaning that if I wanted to know the number of pennies in this jar, that would be the population of all the pennies. But if I wanted to know all the pennies in circulation around the United States, around the world, I could possibly sample this jar to make a prediction about that. So because we are making predictions, we're no longer using the z table. We're actually using the t table. And as the number of samples or n gets larger and larger and larger and goes to infinity, the t table starts to resemble the z table, meaning it starts to spread out more. It looks like a normal distribution. Number 7, the unbiased estimate of the standard error of the mean. Let me just make sure you know this term, guys. That's the standard error of the mean, S of x bar, is going to be, on mine it's the last choice, but it's going to be equal to the standard deviation divided by n minus 1. All right, and this n minus 1 always happens whenever you are using a sample. Previously, it was just over the square root of n. Now we have n minus 1. We're going to reduce our degrees of freedom because we're using a sample. All right, the difference between the sample mean and the population mean. So again, I have the pennies in the jar. If I have the mean of that, right, let's say that's our entire population, and then I have everyone in here estimate the sampling mean, that's called the sampling error. And again, you can never get rid of sampling error. There's always going to be some possibility that the numbers are not going to be exactly perfect. But what we're doing is we're limiting it down to less than a 1% chance that could happen by using a 99% confidence interval. With the degrees of freedom, all right, the larger the sample size, in going to infinity, that means the sample size and the more closely the t distribution is going to look like the normal distribution. So again, as n, the number of samples goes to infinity, gets larger and larger and larger, the t distribution starts looking more like the z distribution. Number 10, the mean of the sampling distribution of means. So the mean of the sampling distribution of means, again going back to that penny analogy, if I take the mean of the sample, everybody's means on the penny, that's equal to the population mean, right? The mean of the sampling distribution of means is equal to the population mean. Number 11, the standard deviation of a sampling distribution of means. The standard deviation of a sampling distribution of means is going to be less than the population standard deviation. And you know that from just looking at the formula. The population standard deviation is this, right? And to get the sampling distribution of means, that's equal to the standard deviation over n minus 1, right? And so already we know, because we're dividing it by some number, it has to be smaller, right? Number 12, through the sampling process, social researchers seek to generalize from a small group to a large group. That is true. That's kind of the benefit of using samples, is that you don't have to spend your time to go out and find something about every single person on campus. Number 13, unfortunately, sampling error cannot be calculated. That's false, because I'm asking you to calculate sampling error over and over and over again. All right? When estimating, number 14, a population mean, the degrees of freedom will always be n minus 1. Degrees of freedom will always be n minus 1. That's 14. Number 15, when increasing our level of confidence interval from 95% to 99%, the interval will grow. Right? It's sort of reverse of the question I asked earlier. All right, number 16, when increasing the level of confidence interval from 95 to 99, when we went from the 95% of confidence interval to a 99% confidence interval. Here, when we do this, we are basically, when you have a 95% confidence interval, what you're saying is, I don't know exactly what the mean is, but I'm 95% confident that it falls somewhere in between this number and that number. Now, is it possible to fall outside? Absolutely, but there's only a 5% chance. Same thing when I have a 99% confidence interval, all right? But when I go to a 99% confidence interval, I am losing my precision, meaning I'm not going to be as exact. I've got a larger range, but I am gaining confidence, okay? So number 16 says, when increasing the level of confidence from 95 to 99, I'm losing precision, right? I'm getting a wider range. However, I'm gaining confidence. I went from 95 to 99. So there is only a 1% chance that I'm off here. But that makes sense because now my range is much larger than it was before. All right, 17 is going to be all of the above. All right. 18, what is the standard error of the mean when analyzing the IQs of 25 adults? Right here where it says 25 adults, your whole population is 25 adults. So my n is going to be equal to 25. And it gives me, and it says given that the population standard deviation of adult IQ is 10. All right, so I know it's 10. I'm going to take 10 divided by the square root of 25. And again, because I got the word population in there, I don't have to do the other things that we were talking about earlier. So I have 10 divided by 5, which is just going to be 2. Right, because it gave me the population standard deviation. When I don't have the population standard deviation, I have to estimate it. That's when I'm going to use the n minus 1, when I'm using a sample. So on number 19, an education researcher is interested in studying student performance on the SAT. The researcher takes the random sample, so here I'm using a sample. Therefore, I'm going to have to use n minus 1. So again, when you do population, you do not need to use n minus 1. You only use n minus 1 for degrees of freedom when you are doing a sample. So I have a random sample of 200 students, and I calculate the sample mean of 1,600. So first thing here, I have 1,600 as my sample mean. I'm going to have n equals 200 because I'm using 200 students. and I'm going to have my standard deviation is going to be equal to 90. All right, to calculate my standard error of the mean, just plug it into the formula. I'm going to have 90 over the square root of n minus 1, which is 199, which is going to give me 6.36. 6.36 is my standard error of the mean. All right, question number 20 is asking me to use the information from 19. It wants to know what's the upper limit of the confidence interval. So a confidence interval just means that you are taking whatever the mean happens to be, and I am going to build a confidence interval around it based on using the standard error of the mean as well as my t-score. So it tells me that I want to do a 95% confidence interval. The problem doesn't tell you what kind of confidence interval to do or what side. Always use 95%. So here I'm going to now take x bar plus or minus 1.96 times my standard error of the mean, which is 6.36. When I do that, this 1.96 times 6.36 is going to be 12.47. And so then I just plug in my number for x bar, 1600, plus or minus. And that plus or minus means that 1600 plus 12.47 is my upper limit, and 1600 minus 12.47 is my lower limit. When I do the math on that, I find out that I am going to have a upper limit of 1612.47 and a lower limit of 1600 minus 12.47, which is going to give me 1587.53. 1587.53. All right, question number 22. A researcher is interested in school violence, investigates to the extent to which conflicts occurred in schools. She obtains a weekly count of witness arguments from 15 students. So she wants to know, how many arguments did you see for the entire school? So she does a sample, all right? She finds 15 students. So the degrees of freedom, because she's sampling, is going to be 15 minus 1, which is 14. That's number 22. On number 23, the easiest thing to do is to calculate the standard. You need to first do the standard deviation. I like to use the raw score method, so I take an Excel spreadsheet, put the numbers in, and square them. So to get the standard error, let's say if I took all the numbers here and squared them, the sum of x squared is going to be equal to 320. This is just the formula I happen to use. Then I take the sum of x squared, which is 320, divided by my n, and I've got 15. And then you subtract, because this is giving me all my error, I'm going to subtract my mean from here, my mean squared, right? My mean in this problem is 4, right? So my x bar is equal to 4. Minus 4 squared is 16, right? This is a quick way to do standard deviation. I think I did one problem or example of it back in the standard deviation chapters. You can use whichever one is easiest on you. If I do this, I'm going to end up with 21.33 minus 16, which is the square root of 5.33, which is 2.30868. Right? So the 2.30868, this right here, that's just my standard deviation, right? Now because I am going to the standard deviation of the mean, I have to take this number and I have to divide it by n minus 1. So if I take 2.308 and I divide it by n, which was here, 15 minus 1, the square root of 14, I am then given 0.617. 0.617 is my standard error of the mean. So now I can go back and figure out what my, for number 24 is, what my upper, and for number 23, my lower confidence interval. So if we go back to the confidence interval, my upper limit, 4 is my mean. My upper limit is going to be 4 plus or minus 2.145, and 2.145 was given in the problem, times 0.617. When I do that, I find out that my upper limit, or plus or minus 2.15 times 0.617, is going to be equal to, and let's do minus first. My lower limit is going to be equal to 2.67, and then 4 plus 2.145 times 0.617. This is going to be equal to my upper limit, which is going to be 5.32, right? So the 95% confidence rule means that if I were to go out and randomly select someone, right, about fighting and see how many fights that they actually saw, I am 95% confident that the person saw somewhere in between 2.67 and 5.33. It's not impossible for someone to be outside, but I'm trying to estimate, so it's a confidence interval. I'm 95% confident that that number will be somewhere in there. All right? The last question, number 25. A sample. So again, when you see the word sample, you automatically know you're going to be using the formula with the n minus 1. Right? So a sample of 450, so n equals 450. Adults found that the average hours of TV watched per day was 2.8 with a standard deviation of 0.3. So my mean is equal to 2.8, and my standard deviation is equal to 0.3. To calculate the standard error of the mean, you just plug in your standard deviation, 0.3, over your n minus 1. All right? So 0.3 divided by 449 is going to give me 0.3 divided by 21.19, which gives me 0.014. 0.014 is your standard error of the mean. All right, look over the homework problems. If you did relatively well, you'll probably do well on the exam. If you still are struggling on them, can you make sure that you do a couple of more practice problems, because remember the exam is time. And so if you are taking the exam and you have not prepared for it, you probably will get frustrated. This is not an exam where you can open your book and try to figure it out. And like I always tell you, practice, 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 and then practice.